Hello friends, my name is Lalit Singh Mehta and today I am going to explain you the concept of thermal stresses in composite bars. So regarding thermal stresses are the stresses which are induced in the body due to variation in temperature, or we can say due to the rise in temperature or the fall in temperature due to temperature variations. So the thermal stresses when induced in a composite bar. So composite means composite material is a material which is the combination of two or more materials. Means when two or more materials are joined together, then the material is considered to be as composite material. So thermal stresses due to temperature variations in composite bars. So let us see the thermal stresses in composite bars and what are the equations governing it. So first, if I draw three cases, or we can say three diagrams. So this is the first diagram in which this is brass and this is steel. This is diagram number A. If I draw the second diagram, this is the second case. I will explain you what it is. Again, this is brass, this is steel, and this is the third case which I am trying to draw now. This is the third case. Brass and steel. So these three are the cases. The first case is, this is a composite bar. Composite bar is a mixture of two material. The hashed material is the brass and this non-hashed portion is the steel or material steel combined together. Then heat or the thermal heat or temperature rises there in this composite material. That's why the brass expands more than steel. Now why brass expands more than steel? This is due to, we can say, alpha or coefficient of linear expansion. So alpha for brass is more than alpha for steel. For this example I am saying alpha of brass, coefficient of linear expansion of brass material is more than coefficient of steel material. That's why on application of heat, brass is expanding more than steel. As we all know that material expands on application of heat, but brass is expanding more because alpha of brass is more than alpha of steel. So this is the second case. Now in the third case we can see, since the brass is expanding more, so it has to be brought down to its, for making it equal in length with the steel, it has to be compressed, correct? That's why this P or this load is compressing it because it is expanding more, and steel needs to be stressed. Some tensile stress will be induced in the steel for making it equal in length. So these three are the cases. A, equal in length composite structure. On application of heat, brass expands more due to alpha. Alpha of brass is more than alpha of steel. And in the third case, we have to make both the composite material equal. Means we have to bring down this composite material into equilibrium. That's why we have to apply some compressive stress to this brass and tensile stress to the steel, since steel is expanding less. So these are the three cases. Now let us See, now we give some denotions. Now let sigma S be the stress in steel, material steel, then sigma B stress in brass, AS area of steel, AB area of brass. Similarly, we can see ES, EB, Young's modulus of steel material, Young's modulus of brass material. T temperature change degree Celsius, L length of composite material, correct? Here the lengths are equal because of expansion. Length of brass is becoming more, but it has to be compressed to make it equal again. So that's why length of composite material is taken as L. Now these are all the assumptions which we have taken for the process. So first we can see that this is the stress in steel, this is stress in brass. So we can say that load on steel PS. Now sigma is equal to P by A, therefore P is equal to sigma into A. So load on steel material can be written as sigma of steel into A of steel, correct? From the denotions we can get it. Similarly, we can have load on brass, it can be written as sigma B into AB, correct? So we have load on steel, sigma S, stress in steel into area of steel, load on brass, stress in brass into area of brass. Now for the equilibrium of the condition, now for maintaining equilibrium balance condition. Now for maintaining equilibrium for the system, this is denoted by PS, this can be written as PB. So now for maintaining equilibrium for the system, this is the equilibrium, means we have to balance the system. Load on steel PS should be equal to load on brass, correct? For maintaining equilibrium of the system, load on steel should be equal to load on brass. This implies that expansion of steel, or we can say tension of steel should be equal to compression of brass. So this is for maintaining the equilibrium of the system. Load on steel material should be equal to load on brass material, but this is happening when expansion of steel or tension is equal to compression of brass. So this is the first case. So we can write this as, this thing can be written as load on steel should be equal to load on brass. So we have already calculated loads. So this can be written as sigma SAS is equal to sigma B A B. Correct? This is coming from here. So we are maintaining the equilibrium of the system like this. Now we know actual expansion of steel is equal to actual expansion of brass. This actual expansion should be equal. Actual expansion for this composite material should be equal. Now we will calculate these two values separately. Now actual expansion of steel can be written as free expansion of steel, correct? Free expansion of steel plus expansion due to tensile stress, correct? Because this thing is very important, please note it down. Actual expansion of steel. Now whenever a material is heated, suppose this is heated at a temperature of T degrees Celsius, so it will expand, correct? This is delta L. So this delta L is nothing but free expansion of steel, free expansion of steel. But with this there is a expansion due to tensile stress, we can see, because it is alpha of steel is less than alpha of brass, therefore it has to be expanded due to tensile stress. This tensile stress is expanding the steel. So there are two factors which are taking place for the actual expansion of steel. Now we know free expansion of steel, free expansion is given by the formula alpha TL. So this is the relation for free expansion. In my earlier video I have already explained what is this free expansion or natural deformation. This is also called as free expansion or natural deformation. So alpha TL. So in this free expansion I can write in terms of steel values alpha S, alpha of steel, into T temperature. Temperature I have denoted capital, so we have to put it capital T here, capital T, temperature, into L, length of the composite material, which is equal. So this is alpha TL. So this is free expansion of steel. Now there is the expansion due to tensile stress. Expansion due to tensile stress Now we know when a material is delta L is equal to PL by AE, correct? This is due to the load P. Now this delta L, P by A is sigma, this P by A is sigma L by E. So this is the, we can say, expansion, or we can say change in length, expansion due to tensile stress, So I can write here, instead of expansion due to tensile stress, this is free expansion alpha TL, and this is expansion due to tensile stress. This expansion is nothing but the change in length, expansion. So delta L, change in length. So I can write sigma L by E here, sigma S upon L ES. So this is, we got the actual expansion of steel, which is equal to free expansion of steel plus expansion due to tensile stress. In the next step we will find actual expansion of brass. Actual expansion of brass. I will keep it up. Now, actual expansion of brass is equal to free expansion of brass, correct? Free, on heating the brass material will expand, free expansion of brass. Similarly like steel, but here the consideration will be, here it is plus, but here in the actual expansion of brass it will be free expansion of brass minus, here it was plus because steel was expanding less, so we have to apply some tensile stress was induced in the steel, but brass is expanding more, so compressive stress will be induced in this. Therefore, free expansion of brass minus contraction due to compressive stress. So this is another major thing which we have to remember. Actual expansion of brass, free expansion of brass minus. Why it is minus? I will explain again. Because brass was expanding more, because alpha of brass is more, so it has to be compressed to bring it to equal length. That's why free expansion of brass. Now free expansion of brass is nothing but again alpha TL. So here we will put alpha TL for brass minus this quantity. So I can write it as, this can be written as alpha of brass into T is the temperature change or rise, into L minus again the same thing, contraction due to compressive stress. Delta L can either be expansion or can either be compression. So sigma LE. So in our case it will be sigma B L upon EB. This is Young's modulus of brass material. This is Young's modulus of steel material. Alpha B, coefficient of linear expansion of brass, coefficient of linear expansion of steel. T is the change in temperature, L is the length. Now we got two equations here with us, actual expansion of steel and actual expansion of brass. Now we can equate this to this and this. Now we can equate, because actual expansion of steel should be equal to actual expansion of brass. So actual expansion of steel is equal to actual expansion of brass. So now we have to put these values there in the equation. Alpha S T is capital T L plus sigma S L E is equal to alpha B T L minus sigma B L E B. This is E S. Now we can see that since the length are same, so length gets cancelled from both the sides. So remaining quantity is alpha S T plus sigma S by E S is equal to alpha B T minus sigma B by E B. So this is So with the help of this equation, we can calculate the thermal stresses in composite bars. So this is the important thing was why brass is expanding more when compared to steel, because alpha of brass is more than steel. Then for making it equal, we have to apply some the material will apply some the fixation will apply some compressive load to the brass and tensile load to the steel. Now because of this, for the equilibrium of the system, PS load on steel should be equal to load on brass, which implies that expansion of steel is equal to compression of brass. Therefore sigma SAS is equal to sigma B AB. So this is equation number 1, we can say, and this is equation number 2. So by using these two equations, 1 and 2, we can calculate the thermal stresses in composite bars. So the major note down point was always check value of alpha. So alpha plays a very important role in this denotation. So alpha S, alpha B, T, rise in temperature, thermal stress, sigma S, ES, sigma B, EB, minus plus the sign conventions I have already explained, plus due to expansion due to tensile stress, negative due to contraction due to compressive stress. So in this way thermal stresses in composite bars can be calculated. Hope the concept about the thermal stress in composite bars is clear for you now, and any suggestions you can comment, and hope you like the video. Do share, like and subscribe my video. Thank you.